Hello and welcome to seminar number 26. It's been a while, I've been busy doing research and stuff like that. And today I wanted to talk about what is pitch blende, uraninite, processing of uraninite again, and why do we need uranium dioxide as fuel and not just metallic uranium. And then I wanted to quickly mention the TRIGA fuel because I think that's quite an interesting type of fuel element. And this whole seminar was inspired by me going on an excursion to the Erzgebirge. You've seen that video, it's already uploaded. And one of the guys who went along was like, uranium dioxide, you said, as I was telling him that this stuff is basically uranium dioxide. And I was like, wait, isn't that the stuff that the fuel is made of? Why do we need all of that fancy processing stuff? Can't we just use that? And I was like, that's a really good question for a seminar because it's quite interesting and it allows me to explain a lot of theory. So here we go. Uranium dioxide is a simplified description of this mineral. In Germany, we still sometimes call it pitch blende, but its more scientific name is uraninite, or we can just call it uranium ore, even though that includes all of the secondary mineral. And that's the stuff that makes pitch blende quite interesting because it's a primary uranium ore and it contains uranium in its most reduced form that is able to be found in nature. So it contains a lot of uranium 4+, whereas all of the other uranium secondary minerals contains mostly the uranium in the oxidation state +6. Not to say that it's pure uranium 4+, but it contains a higher proportion of uranium 4+, but it also contains uranium 5+ and uranium 6+, and of course oxygen. But it's not all uranium and oxygen. It's uranium, it's radioactive. So of course, since this stuff has been laying around for quite a while, all of the decay products of the natural occurring uranium-235 and uranium-238 and 35 series are going to be contained inside of the crystal lattice and inside of the sample that you just found, most likely. But we typically don't find pure uraninite crystals. It's mostly grown in or onto some other type of rock, and it also contains some other elements. So, for example, iron, lead, chromium, cadmium, and we don't want that. We want chemically pure uranium dioxide, most likely with an increased content of uranium-235. So we need to do some chemistry. But first, we find the stuff. We want to get rid of all of the non-radioactive stuff because we want our machines to be processing all of the radioactive stuff. So all of the chunks that are not radioactive can be just thrown out. You can actually use the radioactivity as a marker of whether you want to process it or not, but also uranium-containing minerals tend to be quite dense, so you can make use of that property as well. And then, if you have your good uranium minerals with a high proportion of uranium, you can then start to do chemistry. You get everything in solution, and then you want to get rid of everything in the solution that is not uranium. So, first of all, you need to dissolve it. And for that, most likely, you tend to use hydrochloric acid, sulfuric acid, but it's quite good to also use hydrofluoric acid because hydrofluoric acid is able to dissolve the silicates, which might be able to trap in some uranium. So, for every, I think it was 1 or 10 milliliters of concentrated hydrochloric acid, 1 drop of concentrated hydrofluoric acid. Not to say that hydrofluoric acid is deadly and you should do that. No, you should definitely not do that. And basically you just want to completely dissolve that stuff. And most of the time you want to add an oxidizing agent because if the acid is not oxidizing itself, so if you're not using nitric acid, which in my opinion is the best acid because it's also oxidizing, you want an oxidizing agent, for example, manganese dioxide or iron 3+, for example, because you want to completely dissolve the uranium, and uranium is best dissolved in the oxidation state of +6. And most things in the first acid digestion will go into solution, but of course, if you're not using hydrofluoric acid, for example, you will have a residue which contains the protactinium, tantalum, hafnium, and niobium, and other elements that are not that soluble. But if you add hydrofluoric acid, you will get them also in solution. So you win some, you lose some. And then you want to start precipitating. For example, the first precipitation, which was inspired from the separation scheme of Marie Curie, is she just bubbled hydrogen sulfide through it, because uranium is in the form of the uranite ion, and also thorium, they do not precipitate out as sulfide. But all of the transition metals that are very annoying, they precipitate out quite well as a sulfide. So you have a big residue, and if you centrifuge it and over again, you will end up with a yellow solution, which most likely contains a lot of uranium, a lot of thorium, and maybe some other transition metals that do not precipitate out as a sulfide ion in acidic solution. But then, after a whole lot of precipitation reactions to get rid of all of the non-uranium, you would most likely be able to then go on to the uranium-specific precipitation methods. For example, peroxide precipitation or complexation, which sometimes is already done in the first step if you're using sulfuric acid, which was also an industrial process, and they are quite specific, and then you have most likely gotten rid of all of the non-uranium specific minerals. At this point, you have most likely a very pure uranium compound. If you, for example, dry this up again or just filter that off, this stuff is then free of all of the nasty transition metals and all of the other metals and elements, because, for example, you don't want any neutrons poison inside of your nuclear fuel. So getting rid of cadmium, for example, or boron, these are neutrons poison, is quite good, but it still contains the natural isotope ratio of uranium-238 and uranium-235. So this is just normal chemically purified uranium. It's so-called nuclear grade material, which means that it's free of any neutrons poisons. And it contains the most uranium concentration by volume or weight. Sometimes it's called a uranium concentrate. Sometimes, if it's baked and stuff like that, you are talking about yellow cake. And then you can start with the enrichment process. But some key words which I just wanted to summarize all of this slide is that you first want to reduce the volume that you're starting with. So you want to get most of your chemicals to only extract the uranium and not some other elements that you don't want. So getting rid of non-radioactive rock is quite well. In our lab, for example, I never do experiments with just normal rock, but we have a pitch blender standard, and for that I'm not using more than 100 milligrams per experiment, which is way more than enough to just measure it. And then you want to reduce the number of elements that you carry out during your experiment. So getting rid of all of the transition metals is quite easy, because most of them precipitate out as a sulfide, and then you don't have to worry about these elements interfering with further chemistry. So you want to first do a non-specific separation, for example, ammonium hydroxide, which also precipitates out quite well uranium, is not very specific, because most of the transition metal elements also precipitate out as a hydroxide. Copper, for example, will not, but you get the point. It's not that smart to start with a uranium-specific precipitate, because, for example, the uranyl peroxide contains a lot of oxygen, and it might be able to function as a sort of scavenger precipitation, also pulling away, for example, iron 3+ all of the solution, and you think you did something very well because you did a uranium-specific precipitation step at the beginning, and you don't want to do further chemistry, but it might be contaminated with all of the transition metals that have not been pulled out of your reaction vessel, for example. You might be able to sneak by, if you don't want some nuclear grade stuff, by just washing it over and over again with hot water. But in my opinion, it's smarter to first start with non-specific separation, and then more specific, less volume, lower chance of contamination of the product, and so on, if you want to purify any element, for example. It's not specific just for uranium. If I extract something out of a mineral, I will start with a non-specific separation, and then further reducing the volume that I have to work with, and then going even more specific. So, uranium dioxide as a fuel. So you're going to start with uranium trioxide, enriched in the context of nuclear fuel, because you started with the uranium hexafluoride, enriched, passing through ammonia solution, making the ammonium diuranate, and then you're going to calcinate it again, making uranium trioxide. This is then reduced with hydrogen to make freshly and hot uranium dioxide powder, but it slowly turns into uranium more than dioxide, and the uranium dioxide powder is then mixed with a binding agent, for example stearic acid or polyvinyl alcohol, and the powder is then pressed into a cylinder, heated to 900 degrees C on an inert atmosphere. You can get rid of the binding agent, but it allows just the production of this nuclear fuel to be better. And then these freshly made cylinders are then heated to 1600 degrees C roundabout in a hydrogen atmosphere, because hydrogen is a reducing agent who you want to get rid of some more oxygen, because you want a very good uranium dioxide crystal lattice to be forming, and this is called sintering, and then these cylinders reach 98% of the density, and you are ending up with these pellets, which are, for all practical purposes, very pure uranium dioxide. They look a bit broken because we're using them for chemistry and not for nuclear reactions. So you want uranium dioxide as a material and not uranium metal, because during the operation of fuel, huge neutron flux, huge heat and stuff like that, so you want something that is very heat resistant. And also some of the oxygen is released binding to the fission products, because the uranium, if it's split apart in the uranium dioxide crystal lattice, it forms two new atoms, and you need space for these two new atoms to be bound inside of the nuclear fuel. So it's very important that the nuclear fuel itself is the first and the best barrier for preventing the release of any fission products. So these fission products are chemically bound inside of this fuel, for example, as an oxide. But there are also some other phases which are seen here. For example, the epsilon phase in the nuclear fuel end up with a ceramic cubic perovskite phase, which contains, for example, the plutonium, barium, strontium, and cesium, and other the rare earth elements as oxides, but sometimes you can also end up with a metallic epsilon phase. You can even have some metallic cesium-137 inside of the fuel, depending on burn-up and stuff like that. I'm just a nuclear chemist, I don't operate nuclear reactors. And this metallic phase is quite important, because if you split the uranium dioxide, you started with a charge of the uranium atom of +4, and then the overall charge, because no electrons can get in or can get out per se, needs to be somewhat 4+. And since you are splitting one atom apart, you are going to end up with an overall charge, very simplified here, of +2 per fission product. But for example, cesium, it's not very stable in the oxidation state of +2. We are talking about very long scales, not directly during burnup. You can end up with a whole bunch of very interesting chemicals inside of this. So some of these elements prefer to have an oxidation state of not +2, so you need to compensate for that to kind of balance out all of the charges. And for example, technetium can stabilize the oxidation state of 0, +4, and +7. So this is quite an important element for stabilizing or compensating the overall charge of the fuel pellet itself. Very simplified, right? Don't kill me, please. In general, but also for this slide. Lastly, I wanted to talk a bit about the special stuff TRIGA fuel, because it's a uranium zirconium hydride, and it's very safe, meaning that it's the perfect fuel for making research reactors. For example, the TRIGA, R stands for research, and it's pretty much impossible to make this stuff explode because it has a negative temperature coefficient, which is quite well. If it gets hot, it becomes less efficient at doing fission, so the hotter it gets, the less fission occurs. And this is because the fuel contains hydride ions, and hydride ions do most of the moderation inside of this type of nuclear reactor. So you're not using primarily the water hydrogen to moderate down the neutrons to do nuclear fission, because you need moderated neutrons to do fission, but you are using the hydrogen atoms inside of the fuel itself. Meaning that on average, if you do a fission, the neutrons coming out directly out of this fission have on average an energy of 2 mega electron volts. But you want to get down to 0.025 electron volts. And most of the moderation to these low energies is done via the hydride ions inside of the fuel, and only the last part is done via water. And if the fuel itself gets very hot, heat is nothing else but just particles moving, the lightest particles are going to move the fastest. And the lightest particles are going to be the hydrogen ions. So the hydrogen ions, negatively charged, are going to move so quickly that they are not able to moderate the neutrons, but in some cases make them actually faster, and this prevents more fission because you end up with just less moderated neutrons, so less fission, which is quite nice. With that being said, thank you for your attention and goodbye.